All right, students, today we're going to be taking a little bit of a different step. We're about to turn the corner into some pretty serious discussions on logic. And before we get there, we're going to have to refresh our memories on some algebraic properties that we've hopefully learned somewhere along the way, and see how it is that some of those structures that guided us through algebra are actually going to apply to geometry problems. So please copy down your title, Algebraic Properties in Geometry. Our objective for the day is the student will connect how algebraic properties are used in geometry. Now, there's a lot of algebraic properties, a lot of basic guidelines that make us do what we do on algebra problems. Not all of them are of particular concern as far as the geometry we're getting ready to get into, but there's a handful that we are going to be focusing on. The student will demonstrate the ability to apply algebraic properties to geometric diagrams, and your essential question of the day is, can I apply algebraic rules to geometric diagrams? And the answer to that is going to lie in basically a different question, which is, can I recognize these algebraic problems or properties when I see the opportunity to use them in a geometric problem? Okay, so there are some basic properties of algebra that will be important to geometric structures as well. The first of the properties we're going to have a look at is what is known as the reflexive property. This one seems very much like common sense, but that's just the way some of these things are. Even the rules that are common sense still need to be rules. And the reflexive property basically says anything or object or shape is equal to itself. Okay. Now, typically in algebra, that usually means statements similar to this, like 5 equals 5, or you could even put things in decimal forms, like 1/2 is equal to 0.5, or 1/4 is equal to 2/8. Different versions of the exact same value that are basically set equal to each other. That's essentially what the reflexive property deals with. Okay, but in geometry, we can also apply that to the idea that when we know we have one structure that is exactly equal to another structure, the statement that they are equal to each other is the reflexive property, that two things, or the same thing basically, is equal to itself. Now, that may seem like a really simple thing to say, but consider this possibility here. We're going to be working with a lot of different shapes, doing a lot of different things with them throughout the course of geometry, and maybe we're looking at a shape like this. It appears to be a pentagon, a 5-sided polygon, that has a line segment coming down through the middle of it. But another way to consider this possibility is that it's not a pentagon with a line through the middle. Perhaps it is two quadrilaterals, 4-sided shapes, one on the left and one on the right, and they are simply mashed together in such a way that they are sharing a side with each other, kind of like adjacent angles do. Okay, so if we were in fact working with two different quadrilaterals as opposed to one pentagon, we might find some instances where it is necessary to be able to establish that, like this guy, the length from line segment AB in the shape on the left and the length from A to B in the shape on the right are the same lengths. And as silly as that does seem, we're getting ready to get into something that is very, very deliberate, and you're kind of forced to explain every little thing about every little thing that you know, and that's going to be an important property, being able to establish that one thing from one shape is exactly equal to another thing from another shape, because essentially they are the same thing. The second algebraic property that we're going to need in geometry is the symmetric property. Now, the symmetric property basically establishes the fact that it does not matter which direction you read an equation. So let's consider the possibility that you've worked through a problem and arrived at a statement at the end that x is equal to 7. Well, we've said all along that it really doesn't matter which direction you send your variables in the equations, because it just doesn't make any difference. Well, the symmetric property is the reason why it does not make any difference. If x is equal to 7, then 7 is equal to x. Can you imagine how difficult mathematics would be is if solving the variable on the left to the left side of the problem gave a different result than solving it to the right side of the problem? We would essentially have a never-ending amount of mathematics for us to study. So we're very grateful for the symmetric property that it really does not matter which direction you read an equation. And the same is true when you start reading geometric equations. The length from A to B is equal to the length from C to D. Oh, that's wonderful. And the length from C to D is equal to the length from A to B. So we're basically establishing it just doesn't matter whether you read left to right or right to left. The measure of angle 1 is equal to the measure of angle 2. And that's what that little M stands for when it's put in front of an angle like that, measure. And, of course, the measure of angle 2 is equal to the measure of angle 1. Okay, so you can very much see how the symmetric property can show its face and be used in geometric problems as well. Now, the property of addition as well as the property of subtraction here in a minute, they're very, very similar to each other. These are important. If two things are equal to each other, then adding the same amount to both sides of the equal sign will still give an equal amount. What this says in plain English is if you start off with two equal amounts, kind of like think about the idea of the balance beam on an equation. Okay, the equal sign is like a balance, and the plates on either side of the equal sign are equal to each other. If it is truly equal, then the balance beam is perfectly balanced. It's not tipping one direction or the other. But then if you take some amount in both of your hands, the exact same amount of both hands, and set it simultaneously on both sides of the balance scale, well, the balance scale does not tip one way or the other. You have started off with equal amounts, then added an equal amount to both sides, and you still have an equal amount. That's what the property of addition basically states. Okay, so let's say if you have a value, like we said a minute ago, x equals 7. Okay, we have two values that are equal to each other. And if we were to add any amount to both sides of the scale, both sides of the equation, okay, in this case, plus 2 to both sides. That's what we always say. Anything you do to one side of the equal sign, you must also do to the other side. Then what you end up with is you end up with a new statement. However, the new statement is also still true. Then x plus 2 would equal 9. Okay. Now what you really just kind of saw there was one of your steps of solving an equation kind of going in reverse direction, but that's what you've been seeing. This is a property we've been using for a long, long time. Anything we do to one side of the equation, we have to do exactly the same to the other side of the equation to keep it balanced. That's part of the property of addition. Okay, well, this can also apply in geometric structure. Here we have a diagram. Well, we've got basically a long line segment, A to D, line segment AD, and then we got BC are collinear with A and D. Okay, we've got a couple of line segments that are congruent to each other, the line segment AB and line segment CD, and that's where we're going to start here. Okay, we have the length from A to B is equal to the length to C to D. So as long as if we can add anything we want to both sides of this problem, as long as we add the same amount to both sides. So let's say they both take on this central segment that's in there, the length from B to C, and that length, whatever it is added into both sides. Well, we still have a true statement. Now it is the length from A to C is equal to the length from B to D. Okay, that's the property of addition. Very similar to the property of addition is the property of subtraction, so I'm not going to explain this one in such great detail. Here's the definition of it. If two things are equal to each other, then subtracting the same amount from both sides will still give an equal amount. Okay, so there's our friend x equals 7 again. They are equal to each other. We may remove any amount that we like as long as we remove the same amount from both sides, and then that should still yield a different but true statement. Okay. And of course, this property can show up in geometric problems as well. Here we have a whole bunch of angles attached to a single vertex A. And let's say we have information that the measure of angle BAC, which is the little guy in the upper left, is equal to the measure of angle DAE, which is the little guy in the upper right. Okay, and actually I have an error in my notes. I'm going to stop the video and correct it, and then I'll start recording again. Give me just 1 second. Okay, erase what you had written down there about angle BAC and angle DAE. What I should have had there is angle BAD and CAE. Okay, so if you examine those two angles that are on the screen now, what we have is we have two adjacent angles on the upper left side that make up angle BAD. And then we have two adjacent angles on the upper right side that make up angle CAE. And if you notice in the diagram, those two angles have an angle that is in common with each of them, and that would be angle CAD. By the property of subtraction, we could remove that angle from both sides, or both of the adjacent angles that are there. And we can do that as long as we remove exactly the same amount, and by removing those angles, we end up with the measure of angle BAC, which is the little guy on the left, and it should still be equal to now the measure of angle DAE, little guy on the right. Okay, so the property of subtraction and addition are properties that we have used for quite a while in order to help us solve equations. Okay. Another very, very important property in algebra, and it's going to be tremendously important to us in what we do in geometry, is called the transitive property. Now, a lot of people would consider this one common sense, but even the common sense stuff has rules that go with it, and this basically establishes if one thing is equal to a second thing, and the second thing is equal to a third thing, then the first thing is going to equal the third thing. Okay, so this sounds a little bit like deductive reasoning, kind of connecting the dots from one thing to another, so that's why it may sound familiar to you at this point. Okay, but let's look at a step-by-step progression of what we might have going on here. Okay, you can see we have three line segments that are going on in this problem. And let's say we know that the length from A to B is equal to the length from C to D. Okay, so I mark that in the picture, giving them one tick mark each. And then let's say we also know that the length from C to D is equal to the length from E to F. Okay, so I mark those in the picture, giving them two tick marks each. And you can have increasing numbers of tick marks to show different things in the diagram being congruent to each other. We don't want to give these new guys just one tick mark each, because that would suggest already that all three are congruent to each other. And even if they are, we don't know that just yet. Okay, then if that's the case, the transitive property establishes now that the length from A to B is going to equal the length from E to F. And we can mark that in the picture if we'd like with three tick marks. But as you can see, what's happening here is basically everything is becoming congruent to every other thing. And the transitive property is what connected those dots. A connected to B, B connected to C, so that means that A connected to C. And that's going to be very important in the work that we're getting ready to do, because what we're going to be trying to do is in some cases like a connect the dot puzzle. We're going to relate some information that we do know about to other information that we're trying to figure out. Okay. The substitution property is really very similar to what the transitive property does, but it's worded entirely differently. So let's take a look here. If two things are equal to each other, then they can be interchanged freely for one another in an equation. And you actually already know this. You've used it plenty of times in your travels through algebra, but we'll look at an example, then I'll tell you where you've seen it 100,000 times before. Let's say we're looking at a couple angles here, in this case, angle ABC and angle GHI. Now let's say we have information about these two angles that basically establish that the measure of angle ABC added to the measure of angle GHI happens to be exactly 100 degrees. Then let's say we come across some more information along the way in the problem that establishes that the measure of angle GHI is in fact 30 degrees. Okay, so what we have here is we have one equation that's talking about angle GHI, and then we come across some specific information about angle GHI. The substitution of property allows us to, in that first equation, remove the label of the measure of angle GHI and actually replace it with its exact measurement. And we could do that because we knew measure of angle GHI and 30 degrees were equal. One of them can be taken out and replaced with the other in the middle of an equation, just like you see there. Now, where you've seen this 100,000 times before is when you have solved an equation in Algebra 1. We have often checked our work by going back to the original problem, removing the variable that we just solved for, and instead plugging in the number that we believed the variable to equal. That was the substitution property at work. Since the variable and the number were equal, we could take one of them out of the equation and plug the other one in without damaging the equation. That's the substitution property. Okay, the final thing we're going to look at is something we've already tinkered with a little bit this year, but we haven't really taken the time to state it openly. Well, here it is. Actually, this is 4 different rules. This is the segment addition postulate, the segment subtraction postulate, the angle addition postulate, and the angle subtraction postulate. All 4 rules are very, very similar, so I've just condensed them down into a single rule so we can save some time. Now basically what these 4 guys say is that adding segment lengths or angle measurements works just the same as adding or subtracting numbers. And this is really not any rocket science or anything like that. Okay, we can say things like the length from A to B plus the length from B to C is going to equal the length from A to C. It's really nothing more than addition, which is something we learned in elementary school, applied to a geometric structure like a line segment. And we could do the same thing with angles. We could take little angles and add them up to make bigger angles, just like we took little line segments and added them up to make a bigger line segment. Okay, here we have several angles that are together. Okay, so if we took those 2 angles, a little guy EDF, and added it to the little guy FDH, then we end up with a bigger angle, EDG. Okay, pretty straightforward stuff. Again, I think most of these things you've probably already heard before, or at least have worked with before, even if you didn't know what they were called or had them explained the way they were just explained to you. But they're going to be very important to the work that we're going to do. So that's why we're spending a little bit of time working on that. Appreciate you finding time to get your notes taken care of. Go ahead and take about 30 seconds, skim back over and write your summary. Jot down any questions that you might have, and I'll see you in class.